Okay. Right, at this point you should have got back your second exams, so hopefully you've all picked them up from the TA. The performance on the second exam was rather good. The average is about 84%, so that's a good performance. Do you have any questions you want to ask before I start today's lecture? Okay, we've had a few lectures on tries, and today we're going to really take a look at an important application of tries, and this is in the representation of of tables that are used in the internet for things like packet forwarding or for implementation of firewalls and so on. Okay, right. So the tables we're talking about. These are really sets of, each table is a set of rules, and a rule has two components to it. There's a filter, which is a Boolean expression, and the components of the Boolean expression are really pieces of data that you can find in the header of a packet that's trying to move through the network. Okay. So a filter is a Boolean expression that might be comprised of variables such as the source address, where did this packet originate, the destination, where's the packet going, and it could include things like the port number where the packet originated, the port number where it is going. You could even have the protocol being used here. Is it a TCP or a UDP? You could have even things like the time of day. Okay. So for example, you might make up a filter which says for packets that started or originated at this particular PC. So that's got its own IP address and is going to some other machine somewhere. So you got a destination address, and you might use the time of day. So between 8 a.m. and 5 p.m. Okay. So packets that start somewhere and they're going somewhere between 8 and 5, you may want to handle in some special way. And the special way you want to handle is given by the action. What do you want to do with packets that satisfy the constraints of this filter? Okay. So for example, you may put a rule in your table that says packets originating from the database lab between 8 and 5 and that are going to this web server which is used to download music, well, they should be dropped. Okay. We won't allow you to download songs between 8 and 5 if you're trying to download it from the database lab. Okay. But if it's outside of business hours, we might say, well, that's okay. Right? So, so we could set up a rule which the filter part describes what packets the rule applies to, and then the action part tells what should you do with that packet. So actions could vary, things like drop the packet in the example I just gave you, or it could be forward, send the packet from the current location to a particular destination location. Okay. And the destination that you're sending it to, which you might call the next hop, where does it go to next, may not agree with that, because the way you get from the true source to the true destination may be by going through a bunch of intermediate nodes. Okay. So, so you could have a next hop information. Okay. So if you're sending packets from Gainesville, Florida to Los Angeles, California, and if right now I'm at the router at the University of Florida, well, from here I might send it to a router, say, in Atlanta. And that router might forward it to a router in Texas, which might eventually forward it to a router in California, which might send it to the final destination of the packet. Okay. So, so each of these routers that I'm talking about would have a table of this sort, collection of filters and associated actions, and the actions would be different depending upon where this table is located. So the action for a packet destined for California in the University of Florida router could be send it to Atlanta, but for the router sitting in Atlanta, the corresponding action would not be send it to Atlanta, it would be send it somewhere else. Okay. So the tables are different depending upon the location of the table, the set of rules could vary, and also the set of actions. Right, we've gone through some of these already. Depending upon the type of application, the filters vary in complexity. The most complex filters around generally tend to have about 4 or 5 components to them. So typically a QoS filter, quality of service filter, would include the source, where is it coming from, where is it going, the 2 ports, as well as the protocol being used. But you could get more complex if you want to throw in, say, time of day, for example. Firewall filters typically vary in their complexity. You may have a filter as simple as having only one variable in it, which could say, if you have an employee that's been fired or is about to be fired, you might go in and insert a rule into your table which says all packets originating from this employee's workstation are to be dropped. Okay, so you just have a single variable in that filter, but you could have more variables in the firewall filter. The most common kinds of filters around are simple one-dimensional filters that are based only on the destination address. Okay. So if you're sending packets around the internet, they typically do their job by just looking at the destination field of the header. Okay. So the most studied type of tables are one-dimensional tables where the single field is the destination address. Okay. All right, so let's first look at destination address filters, and then towards the end of the lecture we'll take a look at higher dimensional filters. Okay. Now, a 2D filter, a one-dimensional filter, you could specify that filter in one of many ways. So, for example, you could give a range of destination addresses to which it applies. Okay. So any packet that's going to a destination whose IP address lies between 35 and 2096 is matched by this specification. More typical is to give the filter as a pair, which is an address and a mask. Okay. And the mask here, basically the zeros signify don't cares, and the ones mean that we do care. So wherever you get a 1 here, the corresponding bit out here is important in the address. Okay. So this 0 says, I don't really care what this first bit is. The 1 says the next bit's got to be a 0. That 1 says then you got to have a 1 and you got to have a 1. And then you don't care what it is, and then you do care, it's got to be a 0. Okay. So there are 2 places where you have don't cares. You have a don't care out here, and you have a don't care out there. Okay. But the other 3, 4 bits have to be 0, 1, 1, and 0. Okay. So this specification will satisfy exactly 4 destination addresses. You can vary this through its 2 possibilities, 0 and 1. You can vary that bit through its 2 possibilities, 0 and 1. And so that gives you these 4 destination addresses that are matched by this specification. Okay. Now, in a real filter, it's not going to look as simple as this, because in a real filter, you're generally dealing with, say, IP version 4, in which case these addresses are 32 bits long. If you're dealing with version 6, then they're 128 bits long. Okay. But most of what's out there today is really version 4, so you got 32 bits. Okay. Now, in reality, people don't really deal with filters that are as general as this. If you pop open any commercial router out there, it's really looking at very simple filters, which are prefix filters. So a prefix filter, if you're looking at it in this notation, would have the property that all the zeros are at the right end. So the don't cares are at the right end. The first several bits are fixed. Okay. So for example, here, I've got a 1, 1, which means I care about these 2 bits. They got to be 1 and 0. Then I got 4 zeros. I don't care about the other 4 bits. Or is it 5? I got 5 zeros. Okay. So this one with these 2 1s means I got to match those 2, so I get a 1, 0 star. Okay. And you can convert that into a range. The 10 star, the smallest address it matches is 10 followed by as many zeros as needed to get to your address length. And the largest address it matches is 10 followed by as many ones as needed to get it to a complete destination address. Okay. So a prefix filter can be specified as an address mask pair. The mask will have the property that you're going to have the ones at the left and the zeros at the right, or it can be specified as a range. Okay. So it's really a special case of both of these two types. Okay. As I said, this is really what you're going to find in real-world routed tables, a whole bunch of prefixes. Okay. All right, so an example of a very, very small routed table. Okay. I have a bunch of filters, okay, and of course there are associated actions. I haven't really listed the actions out here. Okay. All right, so we have a bunch of filters which are specified as prefixes. Okay. And so for example, this one here will match all destination addresses that begin with 1 and 0. Now, of course, that's not the only filter I've got in this table that matches addresses that begin with 1 and 0. This guy here also matches some that begin with 1 and 0, except that they got to be followed by 2 more zeros. Okay. So also here and so also there. In fact, every address matched by P8 is also matched by P7 and by P6 and by P4 and by P1. Okay. And that's quite common. If you look into real tables, given a destination address, typically there'll be many filters that match that destination address. And so you need to have a tiebreaker to determine which rule actually applies. Okay. And certainly you could think of many tiebreakers. For example, the first matching rule. So your table is a serial or a sequence of filters. The topmost filter in the table that matches, that's the first filter, is the one that applies. Okay. You can have a highest priority rule, so to each rule you assign priorities. Of the ones that match, you select the one with the highest priority. You could have something called a most specific rule. Okay. So for example here, if a filter is specified as a range, okay, 2, 4, and you got another one that's 1, 6. Okay. Then everything that's matched by 2, 4 is also matched by 1, 6. Okay. But 1, 6 matches some additional things. Okay. So we say this one is more specific than that. Okay. So for example, if you have a filter that matches all the IP addresses in Gainesville, okay, and you have another one that matches all the IP addresses in Florida, then the Gainesville filter is more specific than the Florida filter. So if you got a packet that's going to Gainesville, you'd rather use the Gainesville rule versus the overall Florida rule. Okay. So the most specific rule says if you have something that's more specific than something else, then you'd rather use the most specific one. Okay. Now this rule becomes somewhat ambiguous because you may have filters like this where you do have an overlap. So if you have a packet that's going to, let's say, the destination address is 12, okay, it's matched by this one and it's matched by that, but neither is more specific than the other. Okay. So if you're using the most specific rule, you have to be careful that you don't have ambiguities of this type. Okay. So that leads to problems like, given a bunch of rules, how do you make sure you don't have this kind of ambiguity in there? Okay. All right, the one that's really used in practice for routed tables is the longest prefix rule. Okay. So if I go back to my previous example, so if you have a packet that's matched by P8, P7, P6, P4, and P1, then the longest matching rule would say use P8. And that's the same as the most specific rule, okay? Because the addresses matched by P8 are a subset of those matched by P7, which are a subset of those matched by P6, which are a subset of those matched by P1, which are a subset of those matched by P4. Okay. So the longest matching prefix is really the most specific rule translated into the prefix domain. When you have prefixes, you cannot have ambiguities as far as the most specific rule is concerned, because there's no way for two prefixes to intersect and have and not have this containment property. Okay, so you can verify that on your own. Okay. All right, so typically then what we're dealing with is the longest matching prefix, and of course our filters are prefixes. Okay. Okay. All right, so that's I guess the example that we just went through. Okay. All right, static and dynamic router tables. Now, in the application we're talking about, performance is very crucial. Okay. You need to be able to, if you want to operate at the speed of the transmission lines that are used in networks, you have to be able to process hundreds of millions of packets a second. Okay. And in order to process hundreds of millions of packets per second, you need to have very, very fast data structures to do this. Okay. If you're trying to do it on a single high-speed processor, then you're looking at maybe being able to afford of the order of 4, 5, or 6 cache misses. Okay. So whatever structure you use, it's got to be searchable very, very quickly. Okay. Small number of memory accesses. Okay. Now, as it turns out, you really can't get that kind of performance with the known structures today unless you limit yourself to static structures. So you build a structure knowing the table ahead of time, and you optimize that structure for search. Okay. Now, in reality, your router table is never really static, because downstream nodes where you're trying to send packets to might go down, in which case you got to be able to change the rules in your table. Or new intermediate nodes come up, you want to be able to put rules into your table to account for that. So in reality, the tables do change. Or in the example of an employee getting fired, you have to instantly be able to go in and update your firewall. Okay, so it's not static. Okay, so in reality, things are not static, but for many situations, you can kind of behave like it is static. Okay, and what I mean by that is you have a structure that is optimized for search, and sure, there are changes taking place, but you don't record that change in this structure. What that means is that at times you'll end up sending packets to intermediate nodes that no longer exist. Okay. And that's really not a problem, because if you don't get an acknowledgement back from a node, you can retransmit the packet. Okay. So you can have some failure recovery schemes. Okay. Instead, you accumulate changes as you discover, like some routers are down, you want to put in new rules, take out old rules. You accumulate them in a shadow structure, which can be updated in batch mode maybe every 20 minutes, 30 minutes, whatever your recycle time is, and then you swap this shadow structure with the working structure with some periodicity. Okay. So for a while, you're sending packets where you shouldn't be, but the alternative is everything is slowed down. Okay. Right, so many of these structures that are in use tend to be static, okay, or at least semi-static along the lines that I described, and they're optimized for lookup. Okay. You need to have reasonable pre-processing time required to create the structure, because with some frequency you're going to be creating a new structure. And storage is important. You want to minimize storage, because then you can take this structure and you can put it into high-speed memory instead of into larger low-speed memory. Okay. So the important things here are lookup time. You got to be able to process several 100 million packets a second, and part of accomplishing that is to use high-speed memory, which is expensive, so storage becomes important. Okay. And then, of course, you have dynamic structures. In dynamic structures, every time you get a change, you got to incorporate that change right away. So, for example, of this employee who was going to get fired, you really can't wait 30 minutes from the time you give him a pink slip, because in that 30 minutes, all of your corporate secrets would be transmitted out of the company. Okay. So you've got to be able to change the rules instantly. Okay. Give you some idea of the size of the tables we're talking about. Right, this table really maybe reflects a few databases or a few routed tables. The size of tables actually changes in time. So if you went to a particular ISP and you looked at their routed table at this point in time, maybe they've got 85,000 rules in there, but if you come back 3 hours later, it might have become 90,000 rules because rules were inserted, or it might have dropped down to 70,000 rules. So they do change in time, even if they're working in that semi-static mode. The largest tables that are out there currently are really of the order of 200,000 rules. So this doesn't represent the biggest tables, just some sample of tables. If you represent these tables using tries, like we've been discussing the last few lectures, the number of nodes in the tries tend to be roughly 2 times the number of rules. Okay. Again, the analysis we did in class said that the number of nodes in the worst case could be the length of a key times the number of keys. Okay. Now the length of the keys here, these are IP4 tables, are like 32 bits. Okay. So you really don't get something like 32 times n, you typically get like 2 times n. Okay. Now for a while, the common solution to routed tables was a hardware solution, which was using something called ternary content addressable memories. And basically in a ternary CAM, each bit can be set into one of 3 states. Okay. So in this case, I've got a ternary CAM which has been organized into 2, 4, 6 words, each word being 2, 4, 5 bits long. Okay. Each bit can be either a 0 or a 1 or a question mark. Question mark means don't care. Okay. So this setting, for example, would represent the prefix 0010 star in a scheme of destination addresses being 5 bits long. Okay. This would represent the prefix 01 star. Okay. Now, if you're doing really IP4, these have to be 32 bits long. Okay. All right, so you initialize your ternary CAM with the prefixes that you have, and then when you get a packet, you look at the destination address and you load it into a register. Okay. You press a button and the hardware searches all of its words in parallel for matches with that. Okay. So in one cycle of the CAM, the matching fellows light up. In this case, these 3 fellows light up. Okay. So you got a parallel search of all the words. Okay. Then the CAM is set up so that it's got hardware to select one of the fellows that lights up, and the one that is selected is the first one in the table. Okay. So you can think of it as like 2 cycles of the CAM or 1 big cycle of the CAM. Initially, all the words that match light up, and then the first one remains lit and everybody else dies off, and this becomes the selector. Okay. All right, so you can use this for first word in table match. Okay. You can use it for longest prefix match by organizing this table in order of prefix length. You can use it for highest priority match by putting in the prefixes by priorities. Okay. So search is very quick. It's running at hardware speed. Okay. Inserts and deletes are a little bit problematic. So if you're doing longest prefix match in IP4, then you've really got, you could have, let's say, 32 blocks, okay, if you ignore a 0 length prefix. So here you could have prefixes of length 32, then 31, 30, and so on. And if you want to insert a new prefix of length 32, you could put it in at the end of the 32 block. By putting it here, you'll have to take out the first 31 fellow and move that by replacing the fellow at the top of the 30 block and the 29 block and 28 block. Okay. So with about 32 moves, you could effect an insert. Okay. Or you could do a delete in about 32 moves. Okay. But that's a lot of moves. Okay. But certainly as far as search goes, looks like a great way to go. Okay. Now there are problems with using this with very large tables. First, of course, comes the capacity. Okay, so if you want to represent 200,000 prefixes in IP4, you got to have a CAM with 200,000 times 32 bits. Okay. Capacity of CAMs tends to be around 100,000 prefixes. Okay. There's a cost associated with it. As you can imagine, these things are expensive. There's a lot of hardware in there for the arbitration to find the first one that matched, and also to find to get all of these guys to be searched in parallel. So there's a lot of power being consumed, which means there's a lot of heat being generated. They take up a lot of space on your boards. And if you want to go to IP6, okay, so now instead of 32 bits of prefix, you got 128. Okay, so if you could handle 100,000 prefixes of IP4, you can only do 25,000 in IP6. So your capacity has gone down a lot. If you want to handle ranges, then you got to take each range and decompose it into a bunch of prefixes. Okay, so that gives you an expansion in the size of the table. So very few ranges can be handled. If you go into multi-dimensions, so like if you have source and destination, well then each entry in IP4 instead of 32 bits becomes 64 bits. Okay, so so there are problems with scalability, ranges, and going with multi-dimensions, but there are also other problems in terms of the power consumed and their cost. All right, so there are many other solutions that people have pursued, which range from, well, perhaps which all start somewhere in software, and sometimes that software gets implemented in hardware, maybe as an ASIC, to get you better performance. All right, the solutions which are more software oriented, there's a wide range of them, things using hash tables to give you good expected performance, solutions using binary search trees, using B trees, using priority search trees that we're going to talk about in a subsequent lecture. But the most dominant structure that you see out there is really tries. So let's start by looking at a simple trie solution. We'll call this a 1-bit trie, because here at each level of the trie, we'll be branching by looking at 1 bit of the destination address. And then we can generalize this to higher degree tries like we did in our last lecture. Okay. So in a 1-bit trie, we're going to be representing keys that are of different length. Okay. So you've got a key here which is of length 2, forget the star, a key of length 3, a key of length 1, and 0. Okay. So these prefixes are going to get stored in a 1-bit trie. These are different length prefixes. And we're not going to use the trick of appending a special character at the end. Okay. The strategy is going to be that in each node of the trie, we'll have capacity to store 2 prefixes. Okay. At the root level, we'll store prefixes of length 1. Its children can store prefixes of length 2, prefixes of length 3, 4, 5, 6, 7, and so on. Okay. So each level is able to store a prefix of a particular length. Okay. So P5 stored here, P5 has got to be 0 star. This has to be 1 star. If you begin with a 1, you go on this side. If you begin with a 0, you go on that side. Okay. So this one here has got to be 1 0 star. Okay. There's no 1 1 star, so this part is empty. Okay. This has to be 1 1 1 star. Okay. This is coming here. It's a 1. That's a 0 0. Okay. So it's 1 0 0 star. Okay. So depending upon whether you're a 1 or a 0, you can find your way through. And if once you get to the appropriate level, you just park yourself in that spot. Now, if you want to search for the longest length prefix here, it's fairly easy. Okay. If you're given a destination address, you follow the path given by the address. If the first bit in the address is 1, you go this way. If the next bit is 0, you come here. If the next bit is 0, you come here. If it's 0, you come there. If it's 1, you go there. Okay. All of the matching prefixes will be found on this path. Okay. So you follow a path given by the destination address, and every matching prefix in the table is found on this path. The longest matching prefix is the last prefix you see on this path. Okay. So you keep track of prefixes as you see them, and the last one you saw is the answer to the search. Okay. You can insert a prefix using the same strategy. We know how to insert into a trie. It's fairly simple. And we can remove a prefix with great simplicity. Okay. In fact, the complexity of all of the operations is order of W, where W is the length of the longest prefix. Okay. So in IP4, you'd be running in about 32 units of time. Okay. Now, the unfortunate thing about this is, as you're going down, okay, when you're coming out here, to decide on the next node to move to, I've got to access this field from memory. Okay. So I know which field to get, whether to get the left child or the right child field, because I know the bit in the destination address. So by looking at that bit, I can figure out which field I want, I get it, and then I can move down here, but now I've got to make another access. Okay. So if you're dealing with IP4, you've got to make about 32 memory accesses in the worst case in order to do a search. And that's too many memory accesses. Okay. All right, so to get better performance, okay, we're going to go into higher order tries. Now, the interesting thing about the high order tries that get used in router tables is that they're not the same kind of high order tries we studied in our last lecture. Okay. In the last lecture, when we talked about a trie whose degree was, let's say, 10, like the Social Security trie, well, every single node had that degree. Okay. Here, we're going to vary the degree of nodes. So some nodes might be of degree 2, some may be of degree 4, some may be of degree 16. Okay. So it's really a variable degree trie. And you have two versions here. Okay. Oops. All right, so we'll call these multi-bit tries because we're going to use a different number of bits to branch on. If a node has degree 2, we'll branch on 1 bit. If a node has degree 4, we'll branch on 2 bits. If a node has degree 8, we'll branch on 8 bits of 3 bits of the destination address. Okay. Now, all right, so branching is done using 1 or more bits. But we have two versions of multi-bit tries. One is a fixed stride trie, and this has the property that if you look at nodes on the same level, so all the children of the root, well, they're all of the same degree. They all use the same number of bits. All the grandchildren use the same number of bits, but that could be different from the number of bits used by the children of the root. Okay. So the number of bits used varies by level, but not within a level. Okay, that's called a fixed stride trie. Then you have a variable stride trie where you relax that and say, well, the number of bits can vary within a level as well as between levels. Okay. All right, so let's look first at fixed stride tries. Okay. The number of levels we need in a trie, okay, to figure that out, we've got to have a place for every prefix. Okay. And if you're looking at a fixed stride trie, so if the roots, you're going to be branching on 2 bits, well then in the root I'll be able to store only prefixes of length 2. Okay. And if the children of the root are branching on 3, then in the children I'll be able to store prefixes of length 5. The 2 bits used at the root and the 3 bits being used at the child. Okay. The number of levels that you need in a fixed stride trie to house all the prefixes you have is actually equal to the number of different lengths in your prefixes. Okay. And if you want to reduce the number of levels, what you have to do is you have to somehow control the different lengths. And to control the different lengths, we use a technique called prefix expansion. And what prefix expansion is, okay, if I look at this stuff here, this is what I had before. Well, here there are 7 different lengths. Okay, you got prefixes of length 1, 2, 3. I don't have a 4, I suppose. I got a 5, 6, and a 7. Okay. Now I can come up with an equivalent table which has only 3 different lengths by expanding some of the prefixes. So I'm going to have lengths of 2, 5, and 7. Okay, so all the other lengths have to vanish. Now I've got a prefix here of length 1. That's not permissible because the smallest length I'm going to allow is 2. But the prefix 1 star is equivalent to having 2 prefixes, 1 0 star and 1 1 star. Okay, so I replace this with 2 prefixes, 1 0 star and 1 1 star. I got a 1 1 star here. When I replace it with 1 0 star, it kind of collides with this fellow. Okay. I can't have 2 copies in my thing, but between a 1 0 star coming from here and a 1 0 star from here, this guy's going to win because this is a longer length prefix. Okay. So in this case, my expansion of this didn't increase the number of prefixes. But when I expand this fellow, I get 0 1 star and 0 0 star. And they don't collide with anybody, so you end up with 2 copies now, here a P5A and a P5B. Okay. So you can expand prefixes of a length that don't exist in your trie to the next available length. If the next available length is 1 more, you expand to 2 prefixes. If it's 2 more, you expand into 4. If it's 3 more, you expand into 8. Okay. So by using prefix expansion, I can control the number of lengths in my table, and with that I can control my number of levels in the trie. So this would translate into something like this. At the root, we're going to branch on 2 bits. Then the children of the root branch on 3 bits. If you branch on 2 bits, you have 4 pointer fields and 4 data fields. If you branch on 3 bits, you have 8 pointer fields and 8 data fields. And then the grandchildren branch at 2 bits. Okay. So here you can store a prefix of length 2, here prefixes of length 5, and then here prefixes of length 7. Okay. Now if you want to search this fellow, well, to search this fellow, I'll first look at 2 bits of the destination address, and knowing the starting point of the root, I can compute the field that I need and make 1 memory access to get that field. Okay. Then if it's this one, the data stored here gives me the starting point of this node. Using the next 3 bits, I can figure out which field here is needed. Okay. So it doesn't matter that this node doesn't fit in a cache because we're not going to bring the whole node in. I'm going to get the 3 bits from my destination address, use the start address given here by this pointer, and figure out which field I need, bring that field in, and then that'll give me the next pointer. Okay. So long as each field fits into 1 cache line, the number of memory accesses needed is equal to the height of this structure. Okay. All right, so now instead of 7 memory accesses, I can search that table with 3 memory accesses. Okay. So when you're designing fixed stride tries, you're faced with a design problem really, and the design problem says, I first do an analysis which says I'm going to run this router on this particular computer or on this chip or whatever, and this chip is going to support memory accesses at this rate. I need to be able to process 200 million packets per second, and so I can afford only 4 memory accesses per packet. Okay. So by doing that kind of analysis, you get something which says I need a trie whose height is at most k. So in my example, k was 4. So subject to that constraint, and given my table, I want to find the best fixed stride trie. Best meaning it takes the smallest amount of memory. Okay. Depending upon how you pick the strides, you get different amounts of memory. So for example, I could pick the stride of the root as 32. You need only one access. Okay. But you need 2 raised to 32 fields. Okay. So depending upon how you structure this, you could need different amount of memory. Even if you look at within things of height exactly 3, you could have a stride of 2 here, 3 here, and 2 there. But I could have had a stride of 3 here, a 2 there, and 2 there instead. Okay. And those would require a different amount of memory. Okay. So I want to pick the strides of the levels, having at most k levels, and using the smallest amount of memory. Okay. Now if you go into, I think I'm going to probably skip this part so that we can finish on time. You can set up a formulation using dynamic programming, using concepts of different levels of the trie, covering levels of the initial 1-bit trie that you started with, and you can set up dynamic programming equations. Let me just skip all of this stuff. Okay. And you can solve these equations to figure out the optimal trie, spending about this much time. K is the height of the trie that's permitted, and W is the length of the longest prefix. Okay. So you can find the optimal strides in a fairly small amount of time. Okay. Now there are multiple dynamic programming formulations you can come up with. I didn't really go through the details of this, but there's another one which is a little more complex, and this one runs about 2 to 4 times as fast as the previous one. Okay. Now what's interesting about this whole topic of using tries in the router and firewall area is there's a huge amount of dynamic programming that gets used to build the optimal structures. Okay. Right, if you look at the amount of memory that's taken by the fixed stride trie, okay, for the sample databases we had up there, if you allowed 2 accesses, okay, then it's pretty big. Okay. But if you go from 2 to 3, there's a huge drop in the amount of memory that's needed. Okay. So that seems to kind of be a critical place. Certainly when we go from 3 to 4, there's another big drop, but not nearly as much as out there. And once you go beyond 4, there's not a whole lot of change. In particular, when you're around 6 and 7, it flattens out. And what that tells you is that by paying virtually no memory penalty, okay, if you're flattening out, this is what you were taking even when you had 32 accesses, which meant 1 bit per the traditional 1-bit trie. Okay. So by using about the same amount of memory as used by the simple 1-bit trie, using this scheme here, you can reduce the number of memory accesses from 32 to about 6. So you get a factor of 5 speed up without paying any memory penalty. Okay. All right, this just talks about runtime. Let's forget that. You can go into variable stride tries. So in a variable stride trie, as I said, nodes at the same level can have a different number of bits that they branch on. So over here, I'm branching on 2 bits. 2 bits means I'm covering these 2 levels of my original trie. Then on this side, I got 5 bits, so I'm going to cover all 5 of these levels. Are going to be mapped into this fellow. And here I've got 3 bits, so I'm going to cover these 3 fellows. Okay. Another way to look at it is prefixes of length 2, prefixes of length 7, provided they begin with 1, 0. Okay. And then prefixes of length 5, provided they begin with 1, 1. Okay. You get the same optimization problem here. Find the strides for all of the nodes. Okay, number of bits being used to branch on every node out here, so that you minimize the total memory, again subject to a height constraint. So what you would expect here is that the optimal variable stride tries would take less memory than the optimal fixed stride tries for the same number of memory accesses. Right, so you can solve this using dynamic programming. I'll skip the formulation. Okay. And actually you can get clever about the algorithms and come up with better algorithms for the case where only 2 accesses are allowed, and also for the case where only 3 accesses are allowed. Okay. And if you look at the experimental studies, okay, this is a fixed stride try out here. Okay. Sorry, this is the fixed stride try. Okay. And then you go into variable stride. The butler is just a technique, again, that we talked about when we were dealing with tries, which says that instead of using the try structure all the way down to 1 key, you may stop when you have, let's say, 5 keys or 6 keys and put them in a bucket. Okay. And so the same thing is done out here. You can have memory savings by stopping when the number of keys is, say, small enough to fit in a cache line. Just don't keep branching all the way down to 1 key. So that's a butler node in this particular field. So with 2 accesses, you can get a huge amount of savings over fixed stride tries. With 3 accesses, you can still get good amount of saving. And then the amount of memory saved decreases as you go to higher numbers. So when you get to, say, 7 or so, there isn't a whole lot of improvement in a variable stride try or a fixed stride try. Okay, let's just spend a few minutes talking about higher dimensions. Now, even though filters could go up to 5 dimensions, really for about the largest filters, the interesting case is really looking at 2 dimensions. Okay. A couple of reasons for that. One is that if you just look at the source and destination, and then all filters that have the same source prefix and destination prefix, put them into an equivalence class, well, then these equivalence classes tend to be very small in practice. So they tend to be only like 5 filters in them, so you can put them all in a bucket and search them serially. Okay. So for practical tables, if you use this trick, just play with 2 and regard equivalence classes where the source and prefix are the same, you get a very good solution. Okay. And there's no point trying to differentiate or have a sophisticated structure on the other 3 dimensions. The other thing is, depending upon how people resolve security issues that are being considered, at least for general purpose routers, you may not have access to anything other than the source and the destination. Sure, if you're working on an intra-enterprise router, say you're doing it internally within a company, you can do whatever you like and even read the text or the payload of a packet and use that for routing. But once you get outside, you will not be permitted to read payloads, and some people are arguing pretty vocally that you shouldn't be allowed to see things like the source port and destination port and so on either. Okay. So there are reasons to focus on 2 dimensions. And we've skipped this. When you get to 2 dimensions, you could certainly extend tries to 2-dimensional tries. Okay. So what I've done out here is I've taken the destination prefixes, which are the first ones out here, and represented them with a 1-bit try up here. Okay. Then all of the filters that have the same destination prefix get mapped into a secondary try based on the source prefix. So for example, this would be where you'd store 0 star. Okay. So 0 star has F1 with this source prefix, F2, F3, and F7. Okay. So those will show up here using the destination. So I've got an F7, an F1, F2, and F3. Okay. So you can build a 2-dimensional try in this fashion. Okay. And of course, you could extend this to multi-bit tries. Okay. So for example, here, the destination try, here you're branching on 1 bit, 2 bits, 1 bit. And then the source tries, here I'm branching on 1 bit, here on 3 bits. Here I've just got a single root in this source trie branching on 2 bits. I got a 2-level source trie here branching on 1 bit and 2 bits. Okay. So this leads to an even bigger optimization problem. You're told how many memory accesses are allowed for the search. Build a trie that can be searched using at most that many, build a 2-dimensional trie that can be searched with at most that many accesses. Okay. Again, you can formulate dynamic programming algorithms to build these things. The dynamic programming algorithms known here don't find the true optimal, they find the true optimal under certain restrictions. Okay. But even those restricted ones, similar to what we had for 1-dimensional case, without paying any memory penalty over the 1-bit tries, you can reduce the number of accesses somewhere between 1/2 to 1/4. Okay. But if you're willing to pay a memory penalty, use about 50% more memory, you can improve the performance by a factor of between 4 to 8. Okay. All right, so as far as tries go, there are several applications of tries. An application that has seen a lot of research over the last several years is in the design of router tables, firewalls, packet classifiers, and stuff. And that area has dealt a lot with multi-bit tries with a very heavy use of dynamic programming. There's a lot more to tries than I've been able to get through in this 1 hour. You worry about, say, succinct representation of tries, compact representation, because I guess memory is very important in this application. And while we've optimized here using the multi-bit schemes, there are other strategies. You start with a 1-bit trie and figure out some compact way to represent it. And we haven't talked about those. Okay. All right, any questions? No. Okay.